All right, class, after about a 10-minute delay here, I think I got it figured out, and we can get back started with our functions and their inverses. Okay, where we left off, we were talking about the graphs of them, and if I have a point AB, then BA has to be on the graph of the inverse. Okay, so any point that I have like 3, 0, 0, 3 has to be on there. Any point 2, negative 3, so 2, negative 3, then negative 3, 2 has to be on there. And what you'll find is these points, so let's say 2, negative 3, negative 3, 2, you'll find that those points, 1, 2, 3, 0, 0, 3, you'll find that those points are reflections across the line y equals x. Okay? So you'll see that in inverses. If a function, and you graph a function, you graph its inverse, it should be reflected over the line y equals x. That's what we'll see. But what is an inverse? Okay? Well, what we come to figure out is, here's f of x, there's g of x. What has to happen? When I put them together, when I go f of g of x, when I compose one after the other, I take the output of, say, g of x, and I then put it into f, I have to turn up with where I started. Likewise, when I take g of f of x, I have to start out, get back to where I started. So my input is x, I apply the function f, then I apply the function g, and where should I end up? Right where I started, back at x, at the identity for a function. So one maps me somewhere else. So in this case, we go from a to b. If the function f goes from a to b, then function b has to go from b back to a. And that's what makes two functions their inverses. Okay? So that's an inverse function. Now, there's some pretty important things that we're going to find out about this. And we can look at this graphically, okay? And we can say, do all functions have inverses that are functions? So let's just take this real easy one, y equals x squared. And we take some points here, 0, 0, okay? And like 1, 1, and then like 2, 4. And we think to ourselves, okay, well, if I take the inverse of this, this means that in the inverse function, this will be 4, 2. This would also be 1, 1. And this would be 0, 0. And we're saying that's pretty good. But what I need to figure out, will this inverse be a function? So I say, let's take a look at y equals x. Ooh, that's, okay, well, I guess that's over 1 and that's up 1. All right, so we don't have much to look at here. But when I take a look at this, it goes through 0, 0, it goes through there. It's a reflection, all right? So then these points over here have to be in that quadrant. These points are going to go over here, right? And then these points there are going to be those. And so we're going to go like this. And we're going to say, okay, now, is that green thing, that's kind of a sketch of the inverse, right? So it's a pseudo sketch of the inverse. Is that green thing going to be a function? And you say, oh, the vertical line test. And we say, okay, so this thing is going to be curving this way. And guess what? There's a vertical line and it fails. No, it doesn't work. And so this parabola, that is a function, its inverse would not be a function. So your book kind of sometimes says, can you have the inverse of this function? I usually say, yeah, you can find the inverse of the function, but that doesn't guarantee that that inverse will itself be a function. It might only be a relation. Okay? And sometimes your book says, well, if it has one, so then they're getting to the point where, hey, it doesn't have an inverse. The funny thing is, then they turn around and they make it work so that it will have an inverse by restricting the domain. So for our sake, let's just say, will it have the inverse that will also be a function? And if that happens, the function is called one-to-one. So one-to-one functions are functions, and their inverse are functions. And a quick way to check this, well, let's see, wait a second. If I'm over here 2 and I'm up 4, or let's say I'm over 1 and up 1, I was over negative 1, and I'd be up at 1. And when I go here, this is 1, negative 1. Notice that the inputs are both 1 and the outputs are different things, therefore it's not a function. But I don't have to get the green thing to figure that out. All I have to do is look at the blue graph and go, hey, there is something over here. There's 2 of them at the same height, which is okay for it being a function, but not when I try to reverse it. So a horizontal line test would also work. So I often say, a quick look at a sketch. If you have a sketch of a function, you want a quick look at it and say, well, first of all, I just told you it was a function, so it passes the vertical line test. Then the question is, does it pass the horizontal line test? If it does, it's one-to-one. If it doesn't, it's not one-to-one. Then let's check out how we would go about finding an inverse. Let's prove. That's what we need to do. We told you that f of x equals 2x plus 1. And let's see, we said g of x. We figured that x minus 1 over 2 was its inverse. Let's prove that it is or that it isn't. So let's find f of g of x. Okay, so that will equal, let's see, f of g of x is x minus 1 over 2. Okay, and then that means wherever I see up there, I see a 2. Then I replace the x with the quantity x minus 1 over 2, and then we add 1. Now I simplify. Well, the 2 is only being multiplied by this, so I'll have 2 times that quantity. I'll have 2 times x minus 2 over 2 plus 1. But those are both divisible by 2, so I get x minus 1 plus 1. And lo and behold, that equals x. Now, composition of functions is not unique. I mean, the order makes it unique. You're not always going to get the same thing. But so what I'm trying to say is, I need to check the other order. Because just because I composed f and g, the order I did it is important. So I need to find g of f of x. And so, we need to go over here and say, can we find g of f of x? So let's see, the color for g is blue. So we have g of 2x plus 1. The function g says, hey, wherever you see an x, replace, there's my input x, there's my x minus 1 over 2, so the input is that, so we get 2x plus 1 minus the 1, all divided by the 2. This will equal, okay, wait a second, that will be 0, and I'll be left with 2x over 2, which is, of course, just x. Voila! We have proved or verified that those two functions are, in fact, inverses. And that's a very key important piece here. We can look at it we can look at graphically, and we can say, yeah, it looks like they're going to be inverses because they're reflected over y equals x. We can look at a point and say, oh yeah, they're just flipped around, so that point is on the inverse. But this is verifying and proving it analytically, and the only way to do that, the only way to verify or prove, is to compose f of g of x, the two functions that you think are inverses, and get x, and compose the other order, and also get x. Now both times you have to get x. Not just the same thing, not 2x and 2x, but x, because it has to be the identity. Now the other thing is, we can do what I like to call, we can look in the phone book for the inverse. Okay? There is a way to look up the inverse. Okay? And here is the way to go looking for an inverse. If I say that m of x is, let's see, x plus 3 over, let's see, how easy do I want to make this? Let's go x squared plus 2. Alright, so we're going to go looking for its inverse. Now remind you, this is a parabola, so its inverse will not be a function, but I want to go look for it. Well, here's how I do it. We say y equals x squared plus 2, and now we'll get out the red, which means now I'm looking for the inverse. How do I find the inverse? Just like we do with the points. This has the point, input of x, output of y. This will have the point, switch the 2. So we switch the 2, and then we solve for y. And so this means x minus 2 equals y squared, and then y will equal plus or minus the square root of x minus 2. Now, when I originally graphed this x squared plus 2, you might realize that that's 1, 2, this parabola. Okay, doesn't pass the horizontal line test, right? So, we want to make this be a function that it has an inverse, so let's make it be a function. Let's erase this half. So that means that this half is such that x are less than or equal to 0. Now we take a look here. What numbers do I need? Remember, we want to reflect it across y equals x. I need something here that goes 0, 2, 2, 0. Gives me a negative and a positive, then I'm going to get a positive and a negative. So I need something that will show me this bottom part. Which of these two branches, the positive square root of x minus 2, or the opposite of the square root of x minus 2, gives me the bottom? And the answer is y equals the opposite of the square root of x minus 2. Now, even with that having been said, I think I've found the right Bill Johnson, we'd say here in the States, some very generic name, okay? So insert very generic name here that everybody has in common, right? And then look at this and you go, okay, so I think I've found the inverse. But just because they have that name doesn't mean that that's the inverse. We haven't proved or verified that it's the inverse. You'd still have to compose in order to do that. And we'll end this session. I think I'll have covered most everything in there. If I simply practice one more, we'll just find an inverse. Now, to me, proving is the pièce de résistance. The proving is the verifying. That's where that's all at. But there's something to be said about finding the inverse of something. When I give you something that's fairly difficult, well, I don't know if it's fairly difficult, but this tends to get students, okay? So y equals 3 minus x over 2 is my function that I want to find its inverse. So we go looking for the inverse, and we switch the x and the y. So we say x equals 3 minus y over 2. Now we need to solve. No, this is not the example that I wanted. That's not the example I wanted at all. That's way too easy. How about I need an x down here? There we go. If I put an x down there, now we're talking. Okay, so this means x will equal 3 minus y over 2y. Okay? And now I want to solve for y. The problem is there's two y's. There's a y down here, and there's a y up there, and I have division. So step one is to multiply both sides by that y, because I need to get that y out of the denominator. And so over here I'll have 2 times y times x equals 3 minus y times, well, those cancel, and it's just 3 minus y. Now, how do we solve for y? Here's the key. There's one there, there's one there. Let's get the like terms on the same side. Y plus 2yx equals 3. Let's undistribute that y. Y times the quantity of 1 plus 2x equals 3. Let's divide by that, and y equals 3 over 1 plus 2x. So, we haven't proved it yet, but we're thinking that this is the inverse of that original f of x, 3 minus x over 2l, the modified f of x. Okay? Hopefully, that gives you some idea for your day 5 inverses, remembering that they are built upon the operation and the identity, and that you know the difference between looking at a point, seeing it reflected over the y equals x line, so seeing a graph, finding them, as we did here, and then verifying or proving, which is composing, and finding out that f of g of x equals x, and likewise g of f of x equals x. That is the proving and verifying. Good luck on your work. Thanks for your attention.